So we come to our next question. So we ended saying that we're going to have to look at the depth test and updating the color buffer for opaque objects, but then we skip it and we have to do our own sort if we're going to have objects which, from back to front, if we're going to have transparent objects. So how are we going to accomplish that sort? So we're going to talk about that a little bit now. So the first concept is Painter's algorithm. So Painter's algorithm just means we draw stuff from back to the closest. Why is it the Painter's algorithm? Because I start with my campus, I paint my mountain, I paint my part of my house, then I paint some roof, then I paint my tree in front of that because this paint is already dried, right? So it's just called Painter's algorithm in computer graphics. It just means going back to front. There's nothing else to know about it, except for there can be some issues, right? So what does back to front mean precisely? So consider this case. I have my eye here. I have two triangles I'm drawing, A and B. Which one's in front? Well, I don't know. B's in front here, but over here, maybe A's in front. Or consider this really obnoxious case. Which one's in front? A, B, C. No idea which one's in front. There's no right answer to this. So how are we going to deal with these? So in order to get Painter's algorithm to work, we have to cut our polygons. So if a triangles have these kind of weird cases, we're going to cut them into two parts. So A would be cut into A1 and A2, so that we can say A2 is behind C, but A1 is in front of B, and this kind of thing. So there would be some pre-processing step to cut things so that you don't have this kind of obnoxious thing happening. So worse, suppose we had a sort, right? So suppose we did all of our cuts. Now we're going to have to sort. So if we were in class, I would ask you right now to tell me what your favorite sorting algorithm is and how is it going to work. So you've taken an algorithms class and you've studied your in-log in and whatever big O something sorts that you have, but they've all been in 1D. They assume a single order, right? We've sorted a list of numbers. But now, am I going to sort on X or Y or Z? Well, I want depth, so maybe I should sort on Z. But this is a pre-process, and I don't know where my camera is yet. And remember, when I apply my viewing transform, that matrix is going to rotate my whole world around, and different things are going to end up in the front. So here's an example of that. So here's my camera, here's my objects, here's my Z, and I want to go back to front. So in this case, it would be A, B, C, D, right, in order to render these things. There's no trick here. But suppose we move our eye. So I've now moved the camera over here. And now I want to go back to front. Well, now I'm D, B, A, C in order to go back to front from here. So moving the camera is changing the order. So suppose I've run my in-log-in sorting algorithm on my 1 million triangles. And now I gave the user keyboard control and they started walking around my world and they moved where the camera was at. Shoot, I have to update this whole sort and redo the sort because of the new position of my camera. This is not very desirable if I had a lot of transparent objects that I was having to sort and deal with. So we come to a question of what is a sorting algorithm that's suitable for this 3D space that our objects are in, right? The reason this is happening is because it's not a 1D sort only on Z, right? I really have in this drawing, a 2-dimensional space, and in graphics, a 3-dimensional space. And I somehow need to sort it not only on one dimension, but have a sort which preserves the 3-dimensional nature so that no matter where I put my eye, I can extract the correct sort out of the system in a low computational cost. So now we come to an algorithm called binary space partitioning. In past classes, I've asked homework questions and quiz questions on this algorithm. I think I'm not going to ask you homework and quiz questions on this algorithm because it's much hated. However, I think it's important to still introduce it. And the reason is because in your algorithms classes, you've seen relatively simpler algorithms. And I think this is a nice example of when do I need a more complicated algorithm in order to get things done. So in modern graphics, I really do have to do this sometimes if I have transparent objects, only for the transparent objects, not for all of the objects in the scene. And so how would I do it? So let's take a look at how this algorithm works. So we're going to build a tree, right? So trees always look like this. We're going to take all of our objects in our scene, and they're going to be leaves in our tree. And we're going to have some kind of tree that we want to build. So what do? Step one, we need to build this tree out of our raw objects. So we take all the objects in our world, and this can be in 3D, not just in 2D. We find a cut plane. between these objects. And this cut plane could go through objects, in which case we just split them, or it could be through free space. And then we're going to take all of the objects on one side of this cut plane, and we're going to put them in the tree on one side. So everything on this side of this red cut plane is over here. Everything on the blue of the cut plane goes over here. So we've just divided the world into two sides. Is all this happened. And now we're going to recurse. So we come on the other side. We find another cut plane. We're not worried about these objects anymore because we've recursed. We're only dealing with this subset of things, right? So here we have another node in the tree. We're going to cut. And again, everything on this side is going to go on one side of the tree. Everything on this side is going to go on the other side of the tree. So it looks like a classic algorithm kind of thing. We're building a tree out of this, right? And then we can go down another level, find another cut plane, and divide until we have only one object in each subdivision of the space. And so we know that object can't be in front or behind any other object because we know where it was in the space. And we can finish the other side of this, right? So we were recursing down this, and you know when you get to the bottom of recursion, you pop back up your tree, you deal with the other side. You've all had an algorithms class, so this should sound like a familiar thing. It's only a question of how do we do it. And choosing these planes, you can think of as essentially choosing random planes. I've chosen convenient planes here to make it easy to see what's going on by not drawing them through the middle of objects, but they could easily have gone through the middle of objects. So now we have to traverse the tree. So how are we going to use this thing? Now that we've built it, we have to actually use it in order to do something. So here we have a camera over here in this position. So we come to our tree. We've stored all of our transparent objects over here in this tree. We find the first cut plane, which divides the world into a front and a back, right, relative to the eye position. So now at the time we're going to traverse this, we do get to know where our camera is. We're going to traverse it every frame. So the user's walking around, the camera's moving around, we're going to retraverse this tree. Because tree traversal is much faster than tree building. So we're want to decide, do we render the front or do we render the back or do we render the things that lie right on this plane? Well, we're trying to go back to front. So we're going to do everything on the back side first, and then we're going to do everything on the front side. So here's my back side, all of these things. It's this side of the tree. So we're going to go down the tree this way because we're trying to go back to front. So then we get to our next node. It had a split plane here. And again, we have to decide what's back and what's front. Now, in this drawing, this is more tricky. So with the red one, it was very clear. This is back, this is front. But now I'm kind of off on the side. I mean, some stuff on this plane, on this back side of this plane, seems pretty close to me. And some stuff on the front side of this plane seems pretty far from me. So how can I really say this is on the back and this is on the front? So if you consider the point where the camera is, and you consider any ray coming out of this point, let's see if I can get a little annotation here. So if I consider one ray coming out from my eye, along this ray, so this would be 1 pixel. Somewhere I have my viewing plane, right? And this is my frustum. So I'm considering 1 pixel here that I'm trying to decide. In the direction of this pixel, at some point, this pixel has to cross this cut plane. And it has to be true that everything on the back side of this plane is definitely behind everything on the front side of this plane for this pixel. Now, if I consider a different pixel, say the one that goes through B over here, the same thing is true. At some point, I cut through this plane, and everything on the back side has to be behind everything on the front side. Even though this B object is actually closer to my camera than this E object. Because this E object exists over here on this pixel, over here. So this is a little bit counterintuitive by the way that these planes are drawn, right? B is really closer. So you could say, no, I want to draw E first. It should be the one in the back. But we don't. We're going to draw the things on the other side of this blue, whatever it is on the other side of this blue. We're going to draw that stuff because it's on the back for each pixel individually. Okay, so how do we know which side we're on? Whichever side we're on, so this was the cut plane we're talking about right now. We're talking about this blue cut plane. This is a plane in space. So things could be infinitely close to my eye on the same side that I'm on, right? I could have things that are right up here, right on my camera, blocking the view of everything else. So whichever side I'm on, that's the front, because there could be very, very near stuff on that side. Whatever side I'm not on, that's the back. Even if it's not very obvious about front and back, or this red one was obvious, but I could have my eye right up here almost on this plane, and it would be not very clear from just looking at the picture. The test is which side of the plane are you on? So you do the opposite side of the plane, be on the back first. So we're going to render D. So our drawing order for these objects from this eye position is going to be first D, and then all the stuff that comes on the other side, on the front side of this. So that's going to be these. So I've marked EF. We don't know the order yet. So we have to recurse down the tree to this position. And again, we have a back and a front. So we can see that we're going to do the E back and then the F front. So here's E and then F. And then we can continue recursing down this tree, right? So we got to the bottom here. We go back up to the number 1. And remember, when we were here, we had a back and a front. So we've done this whole back side, and we've got our ordering for doing these. So now we're going to come and do this whole front side using the same kind of algorithm. So we come down, we get to here, and then when we do this front side, we make the same kind of recursive choices about what's on the back of the front. This plane 2 is another one of these where it's not very clear what's on the back or what's on the front. This is the back side of this plane 2. So we're going to render A and B before we're going to render C. And indeed, we see that in our ordering of what comes out here. So this algorithm gives people lots of issues. This quarter, I'm not going to ask you to know or solve things about this, but I wanted to introduce it because you might have to be able to do these kinds of things. If you want to be able to deal with transparent objects in the right way, then you have to go have some data structure that tells you what's closest. If you only have 1 or 2, you could use some other kind of hack method in order to figure out what's closest. And in fact, in your labs, I don't expect anybody's going to implement one of these things. I think you're going to use, something that just checks the distance between your camera and the object and makes an ad hoc guess of what's closer and what's further and does that. And I think that will be fine for most things you would want to do with transparency. Okay, questions about sorting from back to front, Painter's algorithm, BSP tree. Let me scroll back through the comments and see if anybody had anything. Okay, so the question that I see related to this is, what if this camera is right on the cut plane? That's a great question. I don't know the answer. So as with every algorithm, you have to deal with the edge cases. So you're going to have to make a rule that makes things turn out consistently. What is going to be? What should you do? I don't actually know. I'd have to think about this carefully. So I'm sure there's a right answer in order to be able to ensure back to front. And maybe the answer is it doesn't matter. Yeah, I think the answer is it doesn't matter. If I'm right on the cut plane, so imagine I'm on this cut plane 2, then every object either has to be on the left or the right. And for each pixel, those pixels can't interfere with each other. So if I fall right on the cut plane, then the order that I choose doesn't make any difference. Only do we care when there could actually be an object in front of another object. So in fact, it doesn't make any difference. Oh, cute puzzle. I never thought about that problem before. Thanks for asking. I see somebody was commenting on Firefox, Chrome, these kinds of things. This is not really what we're talking right now. It's fine. You guys are chatting about it. Chat about whatever is of interest to you while we're having class. It's a good time to get your classmates all paying attention. It doesn't make any difference. I'm only commenting because somebody says I have a preference for Chrome, but I don't mind. Many of you are doing your assignments in Firefox or Safari or something else. Any modern browser should be able to run WebGL, and indeed that's why we have this class in WebGL. You should be able to run your stuff on your phone. It shouldn't be any trouble. You should be able to run on any platform that you want to run on.